So this video will go over the types of definitions that we use for acids and bases, and these are a little bit historical. They help us think about acids and bases in different ways, and we're also going to talk about which acids and bases are strong and weak and what exactly that means. So the definitions of acids and bases, there's three common definitions that we're going to talk about. The first is called Arrhenius. And I'm going to do these in order. The first is Arrhenius, the second is Bronsted-Lowry, and the third is Lewis, acids and bases. And again, these are a little bit historical. The Arrhenius definition came first, and then there were some problems with it, so they had to redefine redefine acids and bases, and then that also had some problems, and so the Lewis acid and base definition came about. So Arrhenius acids and bases, these are the ones that we think about as typical acids and bases. They're defined by their behavior in water, and we say that Arrhenius acids produce protons, okay? And this makes sense. Most of the acids that we think about are the ones that give us protons, like hydrochloric acid. Falls apart, it dissociates and makes H plus and chloride. And because it gives us H plus, we know that that will lower the pH, and that's the definition of an acidic solution, so that makes sense. Arrhenius bases are the ones that we've been seeing so far, which produce hydroxides in water. So for example, sodium hydroxide, it dissociates like an ionic compound, like that it is, and it makes sodium and hydroxide. And because it gives us hydroxides, it is going to raise the pH of a solution, so that makes sense. So for a long time, this was the only definition, and most of the acids and bases that we think about are Arrhenius acids and bases. The problem happened because some bases, like ammonia and amines in general, which are nitrogen bases, they don't have a hydroxide. They don't have a metal in a hydroxide. They don't follow the pattern, yet they are basic, because when I have ammonia and I put ammonia in water, it raises the pH. So I know that it's a base, but it doesn't have a hydroxide. So they needed a different definition that would fit, that would include these other bases. So that brings us to the Bronsted-Lowry definition, which says that acids are proton donors. So the definition of acids really didn't change. It kind of fits the Arrhenius definition also. But now bases, instead of saying that bases are hydroxides or give us hydroxides, we say that bases are proton acceptors. So that leads us to think about any component that can donate or accept a proton can act as an acid or a base. And some things, and water is a prime example, says that water can act as an acid or a base. And the word that we use to describe that is we say that water is amphoteric. So amphoteric means can act as an acid or a base. So what does this look like when we draw reactions? So we have an acid, like a typical acid, HCl, and we add it to water. And the acid is a proton donor, so it's going to lose an H plus and give it to water. So that means my HCl is now Cl minus chloride ion. It has lost a proton. Water has gained a proton, so we say that water has acted as a base. We use the word act a lot here. We say that HCl acts as an acid and water acts as a base. We don't really say that water is a base because it's not always a base, but in this case it is acting as a base because it is accepting a proton. If I have a base, like ammonia, and I use ammonia as an example, and I add ammonia to water, ammonia is going to accept a proton from water. So ammonia is a proton acceptor, which means it acts as a base, and it makes NH4+, it has accepted a proton. And water, because water has lost a proton and become OH-, we say that water has acted as an acid. So this is a good example of how water, depending on what it's with, can act as a base or act as an acid, which tells us that water is, again, is amphoteric. And notice, just as an aside, ammonia, which is the proton acceptor in this case, and makes NH4 plus, when this happens, it does generate hydroxide, which tells us why ammonia increases the pH of a solution. Because it does make hydroxide, it just doesn't bring the hydroxide all by itself. So the last definition is Lewis acids and bases, which sort of came about because there were some things that were acidic but didn't have protons. So they needed, again, to broaden the definition. And instead of including protons at all, a Lewis acid-base definition says that a base is an electron pair donor. Remember, electron pairs from when we were drawing Lewis structures, so this is the same Lewis. And an acid is an electron pair acceptor. So it doesn't have to be a proton to do this. So this, again, broadens our definitions. When we draw the product of an acid or base, it is typically called an adduct, that's with a U there, or a Lewis acid-base adduct. That's just a terminology that we use. Okay, so you are not going to be expected to predict drawings here and what's going to happen, but you are going to have to be able to label them. So pay attention to the labels that we put on things. So BF3, boron trifluoride, reacts with ammonia, which is NH3, and it will do a Lewis acid-base reaction. And what happens is the lone pair on the nitrogen makes a bond with the boron in BF3. And then the product that we get, we draw this way. Notice I put the new bond that was formed, I put that in blue just to show that this bond is the one that came from the lone pair of nitrogen. Because nitrogen is donating the electrons, we say that it is a Lewis base in this reaction, and because boron is the lone pair acceptor, it is the Lewis acid. And this is our adduct, ADDUCT. Okay, the next example is water, H2O, plus carbon dioxide. So water here has a lone pair, and the lone pair of water makes a bond with the carbon of carbon dioxide and gives us this product, which is the adduct. And again, I've put the new bond in blue. And because water is donating the electrons, it is a Lewis base, and carbon dioxide is accepting the electrons, it is the Lewis acid. So when you analyze these, you always want to figure out which of the two gave the electrons that made the new bond, and that is going to be the base. It's always easier to identify the base first, the Lewis base, and then and label it that way. In the big scheme of real chemistry, Lewis acids and bases are very, very important. So we don't focus on them much in this class, but they are really important in tons of like real life chemistry. The last thing I'm going to talk about, I'm just going to run over this really quickly, is strong versus weak acids and bases. So a strong acid will totally dissociate and make H+. So every single acid, HA, will form an H+. So we say that it has 100% dissociation. And these strong acids are most of the halogen acids, which are HCl, HBr, HI, nitric acid, sulfuric acid. You don't need to memorize these. I want you to know what they are. Weak acids are acids that only partially dissociate. So notice I've drawn the arrow differently, the reaction arrow. Instead of drawing it in only one direction, I draw it what we call a reversible arrow. So most of my acid here stays together and the proton is attached. But some, typically around 5%, anywhere from 2% to 10% is normal, will dissociate and make protons in solution. So it is an acid. It will give me a low pH. It will be below 7. However, not all of it will dissociate. So we are not going to do pH calculations with acids like these because they're complicated. All of the pH calculations that we do are always strong acids. And some typical weak acids are HF because the bond is so much stronger. The fluorine is so small that it bonds more tightly to the proton, so it is a weak acid. And then acetic acid, pretty much all organic or carbon-based acids are weak acids. Another weak acid is phosphoric acid. Okay, bases, same kind of pattern. If you have a strong base, it means everything that dissolves is going to make hydroxide. So we get 100% hydroxide for everything that is dissolved in water. All the metal hydroxides are strong bases. So sodium hydroxide, potassium hydroxide, we really only pay attention to the ones that are soluble in water. If they're not soluble in water, then it's a little harder to define, so we're not going to talk about that. The weak bases are bases that don't fully dissociate to make hydroxide, so all of the amines and ammonia, nitrogen bases are weak bases. Again, you don't have to memorize these, I just wanted you to know what they are.